Hey everyone, in this video I'm going to talk about optimization. And in general what we mean by optimization is finding the maximum or minimum of a function and specifically identifying the value of the input for that function that returns this maximum or minimum. And this is important because many tools in statistics ultimately rely on optimization. So one of the most common ways, for example, to estimate any type of or a lot of general types of models is through maximum likelihood, which is, and we'll talk about this not in this class, but in the following semester. Maximum likelihood estimation is based on optimizing a function, which is called the likelihood function, given the data. And but optimization doesn't only play an important role in statistics, but also plays a role in, in certain substantive fields. For example, economics, or if you're doing formal theory or political economy, a lot of formal modeling relies on optimization, essentially. So in this video, I'm just going to go through the basic principle and just review some of the basic concepts. Okay. So the first thing we have to think about when we try to find maxima and minima of a given function is to find what is called critical points. So potential candidates that might be maxima or minima. But before we get to identifying these critical points, first to kind of clarify what we mean by minimum and maximum, we want to kind of distinguish between local minima and maxima and global minima and maxima. A global minimum is any point where f of x is 0, so x0 would be the local maximum or minimum, or if we're sticking with the maximum here, if f of x0 is larger than any f of x for all x within some open interval containing x0, right? So as soon as there's some interval around x0 where any function value f of x is smaller than f of x0, then we have a global maximum. And of course, reverse, if it's always larger than f of x0, then we have a local minimum. A global maximum, on the other hand, is a stronger condition where basically f of x0 is larger than f of x for a maximum for all x in the domain of f. So that means the global maximum is the kind of the largest function value across the entire domain of our function. And as you remember from our last video, we talked a lot about derivatives and talked about how the first derivative, f prime of x, quantifies the slope of a function. And this is extremely useful because it can be used to check whether the function f of x at any point x is ultimately increasing or decreasing at x, because we get the slope of the function. Ultimately, what this means is that we know, of course, if the value of the first derivative at point x is larger than 0, then the function must be increasing. So it can't be a maximum, is it, if it's increasing at that point. Same for decreasing. So if the first derivative of the function is smaller than 0, it's decreasing. So that can't be a maximum either. But if it's neither increasing nor decreasing, so f prime of x is equal to 0, that is a point where locally the function f of x at that point x is neither increasing or decreasing, and so that's usually one of the critical points that can ultimately be a maximum or a minimum. It doesn't always have to be a maximum or a minimum, but at least it is one of the critical points. So given the function f defined over the domain D, all of the following are defined as critical points. First, we have any interior point of D where f prime of x is equal to 0. So any point in the function that is at that specific point has a slope of 0. Second, any interior point of D where f prime of x does not exist. So this might be the case if the function is not continuous. And then third, any endpoint that is in D. Of course, if our function is only defined for a limited, not for the entire, range of real numbers, for example, but only for a certain sequence, then of course the endpoints of that sequence are also critical points. And ultimately, the maxima and minima will be a subset of these critical points. So the first step is identifying these critical points and then checking additional conditions whether these are ultimately critical points. And we're gonna focus on the first set of critical points, namely the interior points of D, where f prime of x is equal to 0, so where the slope of the function at point x is equal to 0. And in order to make sure or to determine whether this critical point is ultimately a maximum or a minimum, what we can do is look at the second derivative at that point, okay? And if you remember, the second derivative, f prime of x, ultimately identifies whether the function f of x at point x is either concave or convex. It's concave for f2 prime of x being smaller than 0, and it's convex for f2 prime of x being larger than 0. And so to kind of give you an idea what concave and convex ultimately means, it's also helpful to kind of go through the logic, remembering that the first derivative shows the slope of the function, right? And the second derivative is, or the slope of the original function. And the second derivative is ultimately the slope of the first derivative at any point of x, right? So that means if that slope is positive, the slope of the first derivative is positive, so the second derivative is larger than 0, that means that the slope of the original function must be increasing as we increase x, right? So that means we have a curve where the slope as you increase in x gets larger in size. So from x equals 0 going upward, the slope is increasing, right? And of course, this could also reverse. So if we start with a negative slope, the slope is increasing or becoming more or closer to 0 first, and then ultimately increasing, right? So this type of curve, so kind of like, if you think about following this line in a car, you're kind of turning you're turning your wheels to the left, and you're kind of increasing the slope, and that's what we mean by convex, right? Concave is ultimately the opposite. We have a decreasing slope as we increase in x, right? So as we go from -4 to 0, there's the highest slope for lower values of x, and then as we go further and further towards 0, the slope decreases and ultimately becomes negative, and then increasingly negative, of course. So there we kind of, if we think about this metaphor of us driving on that function line, we're turning rightwards, right? And the slope is therefore decreasing as we increase in x. And if we combine these two pieces of information, kind of the necessary condition that the first derivative at that point has to be equal to 0, and then check the second derivative in order to make sure whether we have whether the function is, at least at that specific point, locally concave or locally convex, ultimately we can determine that that specific critical point must be a maximum or a minimum, right? So if f prime of x is equal to 0, so that's the necessary condition first to identify the critical point, and f prime of x, f2 prime of x is smaller than 0, that means the function itself is concave. That means it is a shape like this, where we kind of turn to the right, our steering wheel goes to the right. And that means it must be a maximum, because the shape of the function is something like that, at least locally around that point. On the other hand, if f prime of x is equal to 0 and the second derivative is larger than 0, then the function is convex locally at that point, right? So we're turning left as we kind of drive on this function, and that means it must be a local minimum rather than a local maximum. What happens if f prime of x is equal to 0 and f2 prime of x is equal to 0? Usually what so we need more information because it could still be a point, one of those other critical points that I mentioned on the previous slides. But essentially what is usually the case is that this is kind of a saddle point where, for example, when we look at x cubed, even though the function has locally a slope of 0 for x equals 0 for x cubed, for example, it is not a minimum or a maximum because it's only locally a slope of 0, but it basically is increasing for x is smaller than 0 and is again increasing for x is larger than 0, so it's not actually a minimum or a maximum. All right. Let's go just through one quick example. F of x is equal to x cubed plus x squared minus 5x minus 3. So a classic polynomial function. And now we want to identify the possible maxima and minima of that function. So the first thing we need to do is we need to find the first and second derivative of that function. Of course we can use the power rule that we reviewed in the previous video, where the first derivative of this function is 3x squared plus 2x minus 5. And then we can also compute the second derivative. There's a prime missing here, f2 prime x, and that's equal to 6x plus 2. Okay. And so if we wanted to identify, without even plotting these functions, if we wanted to identify the critical points, we could set the first derivative equal to 0, and we would ultimately identify two separate points where this is the case. And I encourage you to kind of go through that math and use the ABC formula. Or PQ formula, depending. And then you identify 2 points, and ultimately what you'll have to do is plug those 2 points into the second derivative and check whether the second derivative is equal to, or smaller than 0 or larger than 0. Okay, we're not going to go through the math here in the video, but I just want to show you graphically how each of these functions look like, so you get kind of an intuition for how this works, right? So on the left-hand side, I have the original function plotted from minus 2.5 to 2.5, and we have here x cubed plus x squared minus 5x minus 3. Okay, and of course we can directly see there's one local maximum and one local minimum here at minus 1.666 and one at x equals 1. That's a local minimum. Yes, and so the point is, if we look at the slope of this original function, and we look at and then we kind of go through the underlying intuition for the first derivative, we know that the first derivative describes the slope of the original function at any given point, right? So in the initial period, in the initial part here, from minus 2.5 to minus 1 2/3, up here, we see we have a positive slope. It is increasing. So of course the first derivative here is positive, but is decreasing as the slope is decreasing here. Okay, so then we reach this point here, the critical point, where ultimately the slope is equal to 0, and so that means the first derivative is equal to 0. the first derivative then is negative. So we have in the original function, we have a downward trajectory, a downward slope that is increasing up to a certain point where x is equal to 1, where the slope is again 0. So we see that we have a negative slope. The first derivative is smaller than 0 and increases again and reaches 0 again at point 1, and that identifies the second critical point where the slope locally is again 0. First derivative is equal to 0, and then it increases again as the function here has a positive slope again. So slope here is increasing, first derivative is larger than 0. Okay. All right, so we have two critical points, of course, where the first derivative is equal to 0, which is at 1 and minus 1 2/3. Now, is this a global, a local maximum or a local minimum? Of course, visually we can see, but we can also kind of go through the logic, because we know at this point, at this specific point, if you look at the second derivative, 3x plus 2, that is plotted here, we see that the second derivative at x is equal to minus 1 2/3 is negative. This is negative because the first derivative is sloped downwards, which ultimately means that the rate of change in the original function is kind of decreasing. So we're kind of in this rightward turn, and so therefore this must be a local maximum. The other critical point, on the other hand, here the second derivative is at this point is larger than 0. It's larger than 0 because the first derivative is increasing. The slope of the first derivative is increasing. So in other words, we have in the original function, we have a case where the rate of change is becoming more positive, and therefore it must be a local minimum. If we want to further determine whether a global local minimum is ultimately also a global maximum or minimum, there are a couple of things to remember. In general, sometimes no global maximum or minimum exists. So for example, the function that I just talked about doesn't have a global maximum or minimum, since it is basically it goes for x's going towards minus infinity, it goes to minus infinity, and goes to plus infinity for x's getting larger and larger. So this is a case where f of x is not bounded above or below. But there are three situations where we can fairly easily identify a global maximum or minimum. First, if a function only has one critical point, so if x0 is a local maximum or minimum of f, and it is the only critical point, then it has to be a global maximum or minimum, because if you look, for example, at x squared, kind of a or any kind of u-shape or reverse u-shape function, there's only one critical point, and you need a second critical point, or you would theoretically you need at least a second critical point in order to kind of reverse the trajectory of the function, in order to have the function being not bounded above or below that local maximum. Second case is globally concave or convex functions. And I should say in the notes, rather than concave and convex, you sometimes see concave up or concave down, but those are synonymous essentially. So ultimately, if f prime of x is never 0 for the entire range of x, that means the function is globally concave or globally convex. Then there is at most one critical point, and that is the critical point is a global maximum if the second derivative is smaller than 0, and a global minimum if the second derivative is larger than 0. And then third, functions over closed and bounded intervals must have both a global maximum and a global minimum. So if they are only defined over a limited range, then of course there must be a global maximum and a global minimum. All right, so this is it for optimization in the math Prefresher itself. There's a lot more detail about multivariate optimization under constraints. We're not going to go all that much into those details, so feel free to kind of skim that part, and we can talk more about it, but we won't need it in the next 2 semesters. So feel free to skim those. In the next and last video, I'm going to talk about linear algebra, which is a topic that we'll need quite extensively.